Next, let's talk about the conditional distribution. So conditional distribution for discrete case, you can get it from the definition. Let x1, x2 have the joint PMF, P x1, x2. I also have the marginal PMF, the px1, px2. They are marginal PMF for x1, x2. So now I would like to know the conditional distribution. So I know x1 equal to little x1. What is the PMF for x2? So this is a conditional PMF. So by definition, numerator is the intersection, denominator is the marginal. So we can get the numerator is a joint PMF for x1 and x2. Denominator is a marginal PMF for x1. So the conditional PMF of the discrete type random variable x2 given x1 is given by this formula. No, you need to be careful. This guy, it is a PMF. What kind of PMF? What's so special? It is a conditional PMF. So given x1 is equal to little x1, what is the probability related to x2? So you need to use this conditional PMF. Similarly, you can get a conditional PMF of x1 given x2. Some common notation. For example, I can use P12. So this is x1 given x2. Or P21. This is x2 given x1. This is marginal. This is conditional. So this is how we define the conditional PMF. We know x1 is little x1. Now what is the distribution of x2? For continuous case, it's more involved. Now x1 and x2 have a joint PDF. We also have the marginal PDF for x1 and x2. The conditional PDF of x2 given x1 equal to little x1 is given by this formula. So that means we know x1 is a little x1. Now I would like to know what's the distribution of x2. So I know some information. So the numerator is joint PDF. The denominator is the marginal PDF of x1. So this will, if you take the ratio, it will give you the conditional PDF of x2 given x1. Same story. This guy, it is a PDF. This guy, it is a PDF. It is a PDF. It must satisfy two conditions. First, it's non-negative. That's obvious because it's a ratio. Both numerator and the denominator are non-negative. Second, if you take integration over the whole region, it must be 1. We can easily verify this. So if you do integration by definition, so this is a distribution of x2, this is dx2. So dx2 by definition is this ratio. So this term does not depend on x2, I can move out. So you take integration dx2, that's how we get from the joint to marginal. So it is 1. So for given x1, this fx2 given x1, it is a valid PDF. This PDF is called conditional PDF. So conditional PDF can be used to calculate conditional probability. For example, in the last lecture, probability A less than x2 less than B. We know to calculate probability, we should use marginal distribution of x2. That's how we get the probability. Here, if you replace this marginal by conditional, the probability, the corresponding probability you get will be the conditional probability. So it's the probability A less than x2 less than B given x1 is little x1. So you know x1 is little x1. What is the probability of x2 between A and B? Similarly, you can calculate this conditional probability. You know x2 is little x2. What's the probability of x1 between C and D? So you will use conditional PDF of x1 given x2. Similarly, you have the marginal probability. So this you should use the marginal distribution. So conditional PDF is used for calculating conditional probability. Conditional expectation. If ux2 is a function of x2, the conditional expectation of ux2 given that x1 equal to little x1 is given by this formula. So very similar argument. Expected value of ux2. This is what we did last time. This is ux2 f2 x2 dx2. So I'm going to use the marginal distribution of x2 to evaluate the expectation. If you use conditional PDF, you will get conditional expectation. Given x1 equal to little x1, what's the expected value of ux2? Expected value x2 given x1 is the mean. So this is conditional mean. Now expected value x2 minus conditional mean given x1. This will give you the conditional variance. So this is variance of x2 given x1. Of course, you can have, if you expand its square, you will get this formula. So this is corresponding to variance x2 is the expected value x2 squared minus expected value x2 then square. So that's the variance x2. Now let's take a look at the example. Let x1 and x2 have the joint PDF. So this is a joint PDF. 6x2. Support 0 less than x2 less than x1 less than 1. Find the expected value of x2 given x1. So you know x1 equal to little x1. What's the expected value of x2? Now we can calculate first. Let's calculate the marginal PDF of x1. So integrate out x2. You can get the marginal distribution. So the conditional PDF of x2 given x1 is a ratio. It's a ratio. Don't forget the support. Now, once you know the conditional PDF, you can calculate the conditional mean. So conditional mean, using conditional PDF. So you get a conditional mean is 2 over 3 x1. There is an interesting observation. So expected value x2 given little x1, it is a function of x1. That's also straightforward. You give me a little x1, I give you expectation. If you give me another x1, I give you another expectation. So for this problem, this expectation is this guy. It is a linear function of x1. If you replace the condition, this x1, by this random variable, expected value x2 given x1, this become a random variable. Remember, expected value x2, this is a number. It's not random. Okay, so expected value x2 given x1, this is a function of x1. Expected value x2 given this big x1. In this example, this is just 2 over 3 big x1. So of course, it is a random variable. So expected value x2 given x1. This is a random variable. So be careful here. If this guy is a random variable, you can calculate its own mean or distribution or variance. because it's a random variable. So there is an important theorem. I will ignore the proof. If you are interested in proof, check the book. The first result is called the double expectation result. This is double expectation. So this random variable, expected value x2 given x1, it's a random variable. If I calculate the expected value again, it becomes a number. So which number is this? It's just the expected value of x2. The second result is about the variance. The variance of this random variable is always smaller than variance of x2. It's interesting you compare two random variables. One, the first guy is called x2. Another random variable is the expected value x2, x1. So these two random variables, they have the same mean because you take expectation, they're the same. But this guy has a smaller variance. Usually in statistics, if we try to estimate this mean, we would put more reliance on this guy. That's essentially regression. Okay, so x1 is the covariance, x2 is the response. You do regression. Somehow you can reduce the variance.